Okay, so for the following circuit, we have to find this I value that's passing through the inductor. So let's look at the circuit when t was less than 0. And we see when t was less than 0, our circuit pretty much looked like this. So pretty much this part wasn't even connected. So we'll have something that looks like this. Hold on, let me change colors. So we have 10 ohms here, 50 volts here, and then we have a current of IT moving through here, and then it's 1 Henry. Now we're assuming the circuit looked like this for a long time, so that means this short circuits. And now to solve for I, it's just going to be 50 over 10, which is just 5 amps. And that's also going to be your value for I at 0. Because obviously the current passing through an inductor can change instantaneously. So the second we flip the switch to over here, obviously at that instance, the current passing through here will still be 5 amps. So now let's look at the circuit when t was greater than or equal to 0. In that case, we flip from A to B. So our circuit now looks like this. Okay, so this is 1 over 9 farads, 1 Henry, and 5 ohms. And then we have IT moving through here, and that's what we're trying to solve for. So let's do a mesh and have it in the direction of IT. Let's call this I. So it's going to be 5I plus L di over dt. That's pretty much the voltage here, plus 1 over c times the integral of I dt plus VOT. This is the initial voltage at the capacitor. So I want to get rid of this integral, so I'm going to differentiate this whole thing. So this is 5 di over dt plus L d squared I over dt squared plus 1 over c times I. And obviously this cancels out because that's a constant. So let's rearrange this more. I'm going to divide everything by L. Okay. And I'm going to have di over dt to be equal to s. So it'll be s squared plus 5 over L s plus 1 over LC. And this, I can now use the quadratic formula. So this is A, this is A, this is B, and this is C. A being a 1 here. So it's minus 5 over L plus minus the square root of 5 over L squared minus 4 times 1 times C all over 2A. So breaking this up. This is a 2 and this is a 2 here. And this part becomes minus 5 over 2L plus minus. This is the same thing as the square root of 4. And we can pretty much bring the have one square root represent the whole thing. So this part, and then break the 4 up here and here. This and this cancels out. And then if you take the square root of 4, square root of 4 and then square that, we can pretty much just bring that into here. Okay? So that will be 5 over 2L squared minus 1 over LC. Now, if we square all of this and then take this, square root all of that and then square it, well, we have the following: 1 over the square root of LC. Now this is your alpha. This is also your alpha, and this is your omega. this being your damping factor, and this being your undamped natural frequency. Okay, so we can rewrite this as the following. Alright, and this is all equal to S1 and S2. So these two roots. This is your natural frequency. So what we're going to do is find what alpha is. Alpha is equal to 5 over 2L, 5 being your resistance, so it's actually your resistance over 2L, and WO equaling 1 over the square root of LC. So this one, wait, I'll just do it here. Your resistance is 5 over 2 times 1, which gives you 5 over 2 radians per second. And this one, it's 1 over the square root of LC, which is 1 times 1 over 9. And that should give you 3 radians per second. Now, pretty much, we have to check the following. If we notice that your alpha is greater than your omega, then that means it's overdamping. Your circuit's overdamping. And the formula to find current passing through the inductor is going to be IT equals A1 to the power of E S1T plus A2 E S2T. S being, your roots from your quadratic, or like this one. Now, if they're both equal to each other, then that means it's critically damping. And that means your current is going to be equal to A1 plus A2T times E to the power of negative alpha times T. Now, if your alpha is greater than omega, then that means you have an overdamping. Underdamp. Sorry, my bad. Let me try again. When your alpha is less than your omega, that means it's underdamping. And this means your current is going to be equal to your E to the power of minus alpha T times A1 cos WD T. W being W is your damping frequency, and pretty much if your W value is greater than your alpha value, you're going to get an imaginary number. So whatever is being times by your imaginary number, that's your WD value, plus A2 sine WDT. Okay? Now, for our case, we see alpha is less than omega. So that means we're going to be using this one. So let's quickly put everything into here. So we get the following. S12 is equal to minus 5 over 2 plus minus the square root of 5 over 2 squared minus 3 squared. And this will be equal to minus 5 over 2 plus minus 1.658 J. And that's your damping frequency. So let's put everything into this formula. So it's minus 5 over 2 T. Recall your S value was this. This was your S. Sorry, not your S. Your alpha. Then times by A1 cos 1.658 T plus A2 sine 1.658 T. Now we have to solve for A1 and A2 to finish this. So to solve for A1, it's going to be easy. We know that when T was equal to 0, our current was equal to 5 amps. So we can put 5 here and put T to be 0. Okay, and then we see A1 is literally just equal to 5. Alright, so now we can just put that into here. Now to find the second one, it's going to be tricky. So what we're going to do is differentiate all of this. So this becomes minus 5 over 2 e to the power of minus 5 over 2t, 5 cos 1.658t plus a2 sine 1.658t plus e to the power of minus 5 over 2t times minus 5 times 1.658 sine 1.658t plus a2 times 1.658 times cos 1.658t. Okay, so that looks good. And pretty much what we have to do now is find di over dt and the time at that region. Okay, so what we can do is use this following formula over here. So we know the current that's passing through here is going to be this value. Okay, so we're right now looking at when t is equal to 0. We know the current is going to be 5. Okay, now what we need next is the voltage of this value. So notice, wait, hold on. Okay, there you go. So pretty much when t was less than 0, notice how this region of the circuit where our capacitor is. So pretty much we're trying to find the voltage of our capacitor when t is equal to 0. So the voltage of this. When t was less than 0, our voltage at our capacitor was 0 because this region of the circuit did not exist. So when t is equal to 0 and when we flip the switch, the voltage at this capacitor is still 0. So that means this is just going to be 0. So we're going to have the following. 5i being 5 plus L, which is 1, times di at 0 over dt. So di at 0 over dt is equal to minus 25 amps per second. So we're just going to plug that into here. Oh wait, actually I'll just do it on the next line. So this is just minus 25 equals minus 5 over 2 times 1 times 5 plus 0 plus 1 times 0 plus a2 times 1.658, and yeah, okay, so let's bring this to the other side. So it'll be minus 25 plus 5 over 2 times 5 all over 1.658, and this is going to be your a2 value. So let me see what that's equal to. That will be equal to minus 7.539. And now we can find your IT. So IT will be equal to e to the power of 5 over 2 t times 5 cos 1.658 t minus 7.539 sine 1.658 t, and this is in amps, and this is the formula for the current passing through the inductor. Okay, so that's it.